Okay, so we're looking at bivariate data. We're interpreting the residual of a data point into trend line. We're explaining what makes a trend line a good approximation of bivariate data. And we're using that to explain why the LSRL, we'll talk about that, is the best trend line. This is a lot, okay? I'm going to revisit all of these objectives at the end, but these are the objectives that we're trying to complete with today's lesson. Did y'all get back to this lesson on Monday at all?
Yes. Yes.
So y'all completed
Yes.
question 1 here?
Yes.
Yes? Okay. Did y'all finish numbers 2 and 3?
Yes. Yes.
We did finish 2 and 3? Okay, did we finish 4?
No.
Or did we finish 3 and that was it? We just finished 3? Okay, so here's what I'm going to quickly do as a recap. So you need this lesson out on your desk. This is, I don't remember, M1-127 or something. Well, I was way off. What was it? 169? I didn't make the notes in there, that's why. Okay, so M1-169. And so here's what I want us to note and pay attention to. Ms. Estel mentioned that we were struggling with writing the equation of a line. Is that true for some of us?
Yeah.
Yes, a little bit? Okay. I need y'all to pay attention to this. I believe that y'all got an assignment sheet. Oh, she gave them to me and I didn't pass them back. Okay, I'm just going to look at one thing really quickly. Listen. If I'm asking you to write the equation of a line, what is the first thing that should pop to your head? Okay. So if you're trying to write an equation of a line, you should immediately think about y equals mx plus b. I believe, and I know this was several days ago, but last Friday I talked about this fact that if you wanted to get to Bryant-Denny Stadium, are you going to pull out of Hillcrest High School and just start randomly making turns? No. That's going to make it really hard to get there. You might eventually get there, but it's going to be easier if you have your destination in mind.
Yeah.
The destination, the goal here is to get the equation of a line. So write out that equation first. Hey Wesley, can you do this for me? Can you actually sit in the desk next to Karia so it's easier if you just see the board that I'm writing on and showing you information for? Okay. Because once you write that equation up there, what is the first thing that you should pay attention to? The slope, right? What defines the slope? What letter up here? M, right? So an M is equal to, and you write this out to help you get there, right? I'm not just writing letters on a board. I write y equals mx plus b so that I know, hey, I need my slope. I need M. And what are the two different ways to calculate M? Change in y. Wait, change in y.
Rise divided by
Hold on. What is that fraction bar mean again? Divided by the change in x. Or rise divided by run. That way, whether you have a table or you have a graph, you just go, all right, what is my change in y? What is my change in x? Right, again, the end goal, write that stuff out to help focus your attention. Because once you identify your slope, you just substitute that in right next to the x. And then what is b? What do we mean by that? Okay, now to be more specific, what I will point out is it is the y value of the y-intercept. The reason why I'm clarifying that is a y-intercept is a point, isn't it?
Yeah.
I don't care about the x value. The x value of a y-intercept is always 0. All I care about is the y value of the y-intercept. Okay? All I care about is the y value of the y-intercept. Okay? Okay. And all of you could have done different equations, and we should have come up with different equations to identify a slope and a y-intercept. I said for number 2, to make our job easier, all of us should use that equation. Did you all use that equation or did you use different equations?
Yeah.
Use that one, okay?
Yeah.
So when I have 85 degrees Fahrenheit, what did y'all do to figure out or predict the number of customers?
You're gonna do it on a piece of paper when we have.
Okay, but I'm just asking you in general, how can we predict the number of customers if it's 85 degrees Fahrenheit outside?
Oh, depending on the season.
85 at X.
Depending on the season.
Say it again, Bailey.
You fill in the 85 for X.
So remember how the temperature, was that your independent or dependent variable? Remember the temperature affected the number of customers, right? The number of customers depended on what the temperature was. So that means that the X is 85. And if 85 is equal to X, 85 can be substituted, that's the mathematical term, right? Oh, and this is something I mean to mention. I need y'all to hear me on this. I was working at the conference I was at. I was working with some middle school teachers on the 8th grade ACAP test that y'all took last year. A lot of us did. And I need y'all to hear me on this. I know that as a math teacher, I probably need to work on using more common language that y'all are used to build you up. What I mean by that is, Barely, you originally said filled it in, right? Okay. Filled it in is an okay way to say that, but the more mathematically precise way to say it, the more academic way to say it is to substitute it in, right? It's called substitution property. And so please understand, I know as a teacher that I need to work on building you up from fill it into substitution, okay? But I also need you to understand that we've already talked about it earlier today, that math is what again, Jaden? How do we define math? It's a study of something? Okay, so I need you to pay attention. I'm going to have someone else answer and then you're going to answer it again, okay? Okay. Patterns and relationships. Okay, so what is math? Okay, so when you study patterns and relationships, you need to be able to communicate that with other people, right? Which means you need a common language. If we're not using the same terms to express the same things, it can get confusing. And so there is a standard academic mathematical way to talk about things. When you take standardized tests or you take higher level mathematics, if we're not using a precise understanding of mathematical language, it can become more confusing. So please hear me very clearly on that. All right? I know I need to build you all up better on that, and I need to work on it. If I ever say a term that you're like, but Mr. Kinney, what does that mean? Let me know. But I need you to understand, precision in your mathematical language matters. I need you to pay attention. So we're going to substitute 85 in for x, right? So 3/4 times 85 plus 35. So what is y? What did y'all get?
98.75.
Okay. But remember, what is y representing?
Slope.
You think the y-intercept? Look again, guys. Remember, x was the temperature, number of customers. So 98.75, what? Can you have 98.75 customers? And so I need you to hear me clearly on this. Listen up. This is an important part of data analysis and statistics and bivariate data. Listen, that's not completely possible, but notice this key word right here. Predict. Is that going to be exactly what we see?
No, this is what we're thinking.
It's just what we're thinking. It's what we're predicting. Remember, with a mean, right? I think we did the mean of the candies over there. The mean was 17.3 candies.
Yes.
Can someone actually grab 17.3 candies?
No.
No, that's just an average. It's just a prediction, okay? So with data analysis and statistics, there's never going to be a perfect answer. There's going to be what we predict. There's that idea of variability in there. And so what we're really saying is we predict there to be 98.75 customers when it's 85 degrees outside. Okay? All right. So, and then comparing the predictions, because you all use the same answers, didn't really get there. So, identify, so right here. when you originally wrote your equations, or when you originally graphed your equations, did you all get the same exact equation on page 168?
Wait,
Like, look at the graphs that you have on 168 versus the graphs that others in your group had. Did y'all get exactly the same graph?
somewhat.
I mean, were they similar?
Yes.
But were they exactly the same?
No.
No. And so, here's what I want you to understand. You may have noticed, right, that estimating a line of best fit can give different predictions. What y'all have been doing is estimating a line of best fit, also called a trend line. But it's not necessarily the best trend line that there is. What we want to learn about, does it mention it here yet? No. Technology, right, can create prediction equations. And so we're going to use technology to learn about the best trend line, the best line of best fit. Okay, so we have created estimates. We've figured out what we think to be pretty good. But we're going to follow the directions on technology. Now, we'll come back to number 4. Actually, no, this is important. I'm going to pause. I want to point this out. We're going to use technology. We're going to leave this lesson for a little bit. But I do want you to understand that your variables matter. What's the independent variable for this entire task?
Temperature.
Temperature, right? The temperature where? Yes, but I think I heard someone say it in the back over here.
At the shop.
the yogurt shop.
Is it at the yogurt shop? It's outside, right? Because it's not what the temperature is inside the yogurt shop. You go to that yogurt shop because of how hot it is, right? So the independent variable, what letter do we usually use for independent? What'd you say? X. Remember, the x-axis is my independent variable axis, right? So x, the independent variable x, is the temperature outside. Whereas the dependent variable, which letter do we use for dependent? Y. Is the what? Is the number of customers. Okay. So we're about to get into the technology side about least squares regression line. I'm going to pause for a second before we do that. So we're going to come back to this task after we finish that one called squared up. So here's the reason why I bring this up, and I want you to note. We said earlier, right, that X is 85, but it's not just 85, it's 85 degrees Fahrenheit. The predicted Y value was 98.75, but 98.75 what? Customers to that yogurt shop, right? I need you to understand that these numbers are not just numbers. The reason why data analysis and the reason why mathematics matters is because it allows us to talk about the real world. It allows us to make predictions. If you're going to start a new business, do you just want to set up shop and hope things work?
No.
No, that's how you lose a whole lot of money.
Gotta promote.
Right? Well, you got to do promotions, sure, but it also wouldn't make sense. If I have frozen yogurt, right? Would it make sense for me to set up frozen yogurt shop in, say, Canada? Why not? Because it's usually what?
It's cold.
It's colder there, right? And if it's colder there more of the year, are a lot of people going to come to my frozen yogurt shop? No. Do you think anyone's going to go to a frozen yogurt shop when it is negative 20 degrees Fahrenheit outside? So it's important to note the relationship and be able to make predictions. Data analysis and statistics matter because that's just one small example. But if you're going to do business, if you're going to do anything, you need to know how to analyze data. You need to know how to make predictions. Maddie, it ain't that cold in here. You being extra. All right. So there are units in the real world that matter here. Always pay attention to your units. Okay. So I don't believe that y'all have this yet, do you? Okay.
Let's see where it is.
Okay. Let's see, Caitlin, can you go to everybody on this side and pass that out? There's 2 sheets. Listen, you should get 2 sheets. So here, over. Marlon, you wanted to do these 3 over here? Okay, so make sure that they get both sheets. They're right behind each other. Okay, they should say square it up. It'd be number 1 here and number 10. So like that's Aiden's. Okay, go ahead and get everybody on that side. Okay. So it'll be easier, just hand them out 2 at a time. While they are doing that, I'm going to send out the file. I say make sure you get the 2 different pages. 2 different pages. Andrew, did you get it? Everybody gets both pages. They're 2 different pages. Did you give it to Andrew, Caitlin? Okay. Please look at your calculator. You should have gotten a file. Go ahead and open up that file on your calculator.
Are these the paper?
That's why. Oh well, it's number 4 was over there. Okay.
We need some.
Thank you. I didn't realize I was under there.
We need
Yeah, let's go. Okay. Are you logged in? So, go to browse. Hey guys, don't forget, excuse me, I'm talking. If the file does not pop up when I tell you it's going to pop up, when you go home, under Documents, hit Browse, go to this class, and it'll be there in this class, okay? So if it doesn't pop up, you go to Home. Dude, it popped up for you. It literally told you the file name. Did you get that group right there? I got it. I just wanted to ask. Okay? So this would go behind, actually, honestly, this would probably best go behind at M1-70. The squared up task should almost go in the middle of this lesson after page M1-70. Because this is to help us answer those questions on M1-70. Did I actually give it to you? There's M1-70. It should go right here. Guys, it should go in between M1-70 and M1-71. Okay. So, that's not what I want. I do want to point this out very quickly before we get started. If I can find the remote, there it is. You need to have out this paper. Okay, so I have this out right now, but I want to quickly point this out. Here, nope, that's not what I wanted. Just kidding. It's not in there. I already told you we're looking at the best what? Best line of best fit. But it's also called the best trend line. That line of best fit is also called the trend line. And so what we are about to look at is, okay, so what line is that? In the textbook or in the lesson that you were given from the book, it just tells you straight up without actually explaining it much. And so this lesson is to help us understand what it means. So, the spreadsheet on page 1.2 displays the life expectancy for men, women, and people in the U.S. for every 10 years from 1900 to 2000, and each year from 2001 to 2004. And we're going to look at the relationship between the year and the life expectancy for a person. So what they're referring to is if you go to 1.2 here, right, you should see, what's this kind of page called again? List and spreadsheets. Hey, make sure you actually have it pulled up on your calculator. You open up the file that I sent. Okay? And you're supposed to be on, if you didn't get the file, browse your documents and go to this class and it'll be there. So, oh, it still doesn't have you logged in for some reason. It's so weird. That's it. That's fine. Oh, open that. For some reason it now has you logged in. That's it. Okay. So, everybody have this list and spreadsheets page open? Yes? I'll say those yes. So notice we have the year in this column. What is column B referencing? What about a person? Close. No. How about you look at the paper again? You're very close, Joey.
Life expectancy.
It's the what?
Life
It's the
expectancy.
life expectancy of a person. Okay? So guys, please notice, it very clearly says person up here. But can you type out life expectancy of a person right there? No, that's too much, right? So we got to pay attention to the sheets given. So in 1900, how long did a person expect to live?
49.2 years.
49.2 years, right? In 1900, how long did men expect to live?
47.9.
All right, but as time goes on, what happens to that life expectancy?
It keeps going up.
Keeps increasing. Now, there's a reason why. It's not the focus of today's lesson. Does anyone know why life expectancy continued to increase?
Medicine.
So, medicine definitely helped us not die as much. What else?
Technology.
Technology made a lot of that possible.
Cancer.
Better resources. Do y'all know,
Nobody helping us.
does anyone know the most frequent age that people actually died in the early 1900s?
20 and 50.
Listen to the question. The most frequent age.
0.
There were more common deaths when babies were born at that time because they didn't have the medical technology, right? So that age 0 to 1, 0 to 2 was actually a very it was a very likely time for people to die. If you die really young like that, does that drop the average life expectancy?
Yes.
Yes, right? So those are things to be aware of. So yes, there's what we're studying, but there's also a reason why behind these things. This is actual data. Thank you very much. Okay? Now, what we are looking at, all right, that's to establish the background of life expectancy. It now says move on to what? What does it say on the sheet and on the board? Thank you, guys. Look, we just read this information, right? Continue down. What does it say?
Move to
Move to page 1.3. Follow the directions on the sheet of paper. It is designed to help get you to what we're trying to learn. So now I'm going to move to 1.3. Again, follow the directions on the sheet. What's the issue? Can I? Okay.
Two different persons.
So guys, Jaden, it helps to have that calculator in hand. You still on page 1.1. And you're supposed to be on what page right now? No, you're on that page, on the document, or on the Word doc. Guys, I cannot help you if you're not following along. Okay, so we're on 1.3. We're still on the very first page of the paper I passed out, or Caitlin passed out, and Tamarlin passed out. We're on page 1.3 of the calculator. Now what does it say? On the data and statistics page,
Credit satisfied to administrator.
okay, I want y'all to notice, you don't need me to tell you what to do here. Follow the directions. This is not something I created. Someone much more intelligent than I did created this. So what are you going to do on this page right here? Right, but so what am I going to do first? So put years on the horizontal axis. So how am I going to do that? Now there's one detail that's missing, but it kind of shows you on this page. You're going to click what? Oh, click to add variable. What variable?
Year.
Year, right? It tells you on the calculator. It says click to add the variable. You click to add a variable on the x-axis. We're going year.
Yeah.
So we got our years there. What are we now going to do?
Illustrator.
So go to y-axis where it says click to add variable and click person. So this is a beautiful aspect of these calculators where, and this is the beautiful part about technology, it's not about just creating a scatter plot, right? What matters more is your ability to interpret the scatter plot, to explain what does the scatter plot tell us. So as we're just naturally looking at this, as the years increase, what do we notice?
It increases the life expectancy.
Well, the life expectancy increases. And here's the reason why I say it that way. Does the year cause the
No.
life expectancy to increase?
No.
The technology and the medicine cause.
And what were you saying, Joey?
That's what I was going to say.
Okay, so you're about to say the technology and stuff. Right, it's the technology does it. But what we should notice is as the years increase, so does the life expectancy. They're correlated. One doesn't necessarily cause the other. Okay? And so there's a thing called correlation versus causation. There's just a relationship. There's a correlation there. And I have to ask, what kind of relationship does that look like? What does that shape remind you of?
A positive line.
So if you're talking about a slope, you're talking about a,
Positive line.
not a positive line, just a line, but what is positive? The slope. That's what you would want to say, right? It's a line with a positive slope. Is it a perfect line? No, because the real world is not perfect, okay? The real world is messy. The real world has variability in it. But we can make predictions off of this. So, I want you to continue. I actually already answered number one. So write your answer to number one. What's the relationship between those two variables?
As the years,
So as the years increase,
the life expectancy.
the life expectancy also increases. At what kind of rate? With what kind of shape?
With a positive.
With a linear, with a positive
Linear.
slope. Right? We would want to notice like that relationship is increasing like a line with a positive slope.
So as the years increase,
So there's two different statements I'd probably make here. As the years increase, well, actually I would say as the years increase, the life expectancy, and I will point out, does anyone know what group of people we're talking about here?
we're talking about like the older.
Pilgrims in the
Pilgrims in 1900?
That was not.
Nah, you tripping.
True. Okay, look up here, guys. There's a detail that we could add into which people group we're talking about.
Baby boomers.
Before the boomers.
Millennials.
Okay, I gotta point this out. Hold up. First off, millennials is my age, not 1900. Second off, are we talking about all people in the world?
No.
Who are we talking about?
That specific year.
Which specific? No, not everybody in
The
the world.
poor. The poor.
Say that again. The Americans. Sorry, I missed you, Marlon. I hear you now, though. I got you. Okay. Look. Okay, we're not talking about Europeans. We're not talking about Asians. We're not talking about Africans. We're not talking about South Americans. We're not even talking about Canadians. We're just talking about Americans here. Okay. So. What friend? Jaden. You ain't got nothing written down. Come on, focus. As the years increase, the life expectancy of who though? Of Americans. Also increases. And I think we also talked about it in a line, right? So linearly is the term there. I know that's really awkward, but the term would be linearly to be an adjective. Hey, Ezra. Hey, Ezra. Ezra. So the life expectancy of Americans also increases linearly, noticing that it's creating a line. And notice I don't have to say it has a positive slope, because if they're both increasing, it would have what type of slope?
A pilot.
A positive slope. Okay. So that's what we could write there under number 1. What are your questions before we continue? Ezra. All right. What are your questions for number 1 there? Linearly just means in a linear fashion. Okay. Linearly just means in a linear fashion. Okay. So I need you to follow these directions here, right? Actually, hold on. I think that might be. Oh, I don't have them in the slides. Do you see that gray box there, right, where it says add a movable line?
Yes.
It's at the very bottom, just below number 1.
Yes.
Follow those directions. And I flip it over. Right there. That gray box under number 1, follow those directions to add a movable line onto that graph.
Wait, on this?
Yes, on the calculator. Follow the directions on that. Under number 1, there's a big old gray chunk of text. That's what it should look like. Janiyah, have you done the directions to add the movable line? Joey, have you added that movable line? Hold on. You don't need to move it yet. It's just a movable line. It should look like that. Yes. Don't do that yet. Hold on. So, if you did not see it earlier, once you hit menu, you need to click what?
Analyze.
That's what it says in the directions.
Move a line.
And add movable line, right? So, I'm going to remove mine so I can add it back in, right? So, menu, analyze, add movable line. It should give you an equation right there, too.
Yeah, I got that.
No.
Okay, so you didn't follow the directions earlier.
How do you move it?
Never added the variables, of course. You didn't notice that when you didn't have that linear relationship there? Okay, so you should add that movable line. Anybody need me to go back through that so that we know how to get the movable line, or so that we have the movable line?
We did this last year.
Good. Did you have Ms.
Miss
Colson?
Williams.
Ms. Williams, yeah.
I know I used to have therapy.
Alright, hey. Hey, stop. I'm trying to teach. Okay. So, if you're confused, make sure you read the gray box on the sheet. It tells you exactly how to add movable line. Talk to someone next to you if you need to. Alright, next is where we go to the back side of the paper. After you get your movable line, you can go to this part where it says analyze the residuals. Now, follow the directions that it tells you. And we'll talk through some of this stuff in a second. You don't see what? Now flip your page over. Guys, you should be on the second page. At the very top, it should say analyze the residuals. And then once you get those squares in there, start looking at the box part and number 2. Follow the directions. Analyze the residuals. Dude, it tells you right here. Analyze the residuals. Read that statement.
I need my finger a little forward.
Did you read this document in the first place? Did you get it correct? current. And so you hit number 4. It's the document you're currently on. So click on add variable. And what are we adding in? No, put it up. Thank you. You're adding the life expectancy of people in the U.S. So put a person. And follow these directions to add a movable line. Okay. So, hey, we should have our movable line in there. We should have our residuals. Now, analyze. Actually, does anybody need me to walk through this because we couldn't follow the directions?
No.
Okay, did you get your movable line in there, Joey? You guys movable line, Emily? Okay, so Joey, once you have the movable line, hit menu, you go to analyze, you go to residuals, and show residual squares. Okay? Now, I need y'all to pay attention to this because this is a really cool detail about these calculators, and it's the point of what we're doing today. What kind of line was this again? Sorry, what was the name of the line when we added it in? It was a what was the button we clicked in the calculator to add the line? It's called a movable line, which means we should be able to do what to that line? Okay, so I need you to pay attention to this. You see my cursor? I know it's hard to see. You can see it better on the TV. But you see how it's right above 0.344x?
Yeah.
If I take that cursor and I put it in the middle of the line, to Marlon, what shape does that cursor become? You see it?
X.
Well, it's not quite an X.
With a whole bunch of arrows.
It's got arrows on it. What should that make you think of if it...
You can move it.
Right, but what should that make you think of? The axis, right? Or maybe like a compass, but it's like the axes, right? So if I put my cursor in the middle of that line, I can hold the control button or the touchpad down, and now I can move that line up and down. Okay, see how I can move my line up and down? That's from the middle of the line. So if I move the cursor towards the end, what does it now look like? If I move the cursor towards the end of the line, what does it now look
like
like?
a reverse.
Okay, maybe a reverse symbol, but it kind of creates that wheel effect.
We don't reverse card.
Okay, we don't reverse card, but what's that going to do to my line?
Reverse it.
Not reverse it, it changes the...
Size.
The degree.
But what does it do to the line?
Change the degree.
Look at that line again. What's changing?
The slope.
Say that louder.
The slope.
The slope is changing, right? I'm changing the slope of that line. So when I'm in the center, it's moving the line up and down. And then when I go to one of the ends, it's going to rotate it. Okay? I want y'all to take just a couple of minutes playing with that tool because you need that tool to be able to get further with the lesson in a minute. Wesley, have you moved your line around at all yet? Listen, this is exactly in the same spot as when you click on Add Movable Line. Okay. So one thing to be aware is once you're done moving it vertically, you have to hit Escape, and now you can rotate. Hey guys, I forgot to mention this. Once you've done moving it in one direction, you have to hit Escape so that you can get off of it and then change to the other one. Have you been moving it around at all? Huh? Oh, it's really close to what it started at. Okay, show me that you can move that around. So you never added this here. Great. here. And add your middle line. Follow the directions.
Okay, but so you ain't going to flex no more? They got me going to
Don't let it be that far.
I gotta do it in 6 weeks if I
You don't want to put those.
It wasn't like it.
don't.
No, get rid of the other one.
Oh, you swear?
I broke my ankle.
Follow the directions. Analyze.
And I got to go,
Residuals.
I walked in.
And show residual squares. How what? Well, notice how it tells you right here that a square will appear at each data point. That's what those squares are. See how those squares are there on those data points? Does that make sense then? Okay. Are y'all able to move your line around, both rotate it, change the slope, and move it up and down?
Yes, sir.
Okay, yes ma'am?
My boss is
We're about to start right now. So try to hold on just because we're about to go over an important skill. So then you have to go to the edge.
in the back. When you look in the first,
You have squares.
So you go to the end here. See how the symbol is now that wheel? Now you can rotate. Okay. And guys, the directions, hey listen, shh, please listen. I forgot to put them in the slides, but if you look at the directions in gray, it tells you how to translate it up and down and how to rotate it, changing the slope. So that first page has all those instructions in there. I mean, don't think about it quite like that. I see what you're saying, but don't think about it like that. Okay, so right here, I need y'all to hear me on this, right? What we're about to talk about are the residuals, and the residuals and understanding the residuals. Am I talking? Thank you. The residuals are important to understand what's happening, because what you just added were the residual squares. Those are the square shapes that you're seeing on the calculator. But those squares are determined by the residuals. Y'all need to know what the residual is then, right? Yes?
Yeah.
Thank you. Okay. So, the side of the square is equal to the value of the residual. The residual is the actual value minus the predicted value. So I want you to note what that is referring to is this. Do you see how here is a point?
Yes.
Do you see how there is a length right here?
Yes.
Yes?
Yes, sir.
Okay. And so that is the residual. The distance from that point down to here is the residual. So the distance, well, and really, I'm going to say this, is from the point to the line. Okay? And I'm going to talk about why that distinction is important in a second. Now, I'm going to go ahead and tell you, I need you to hear me on this. If I have the absolute best line of best fit, let me ask this. Do you think that is a better line of fit, or this is a better line of fit?
This.
The first one?
No, that one.
I said this.
Second, that one.
You think that one currently on the board is better than this one?
Yes.
Wait, no.
Which one fits those points better?
That one.
That?
That
Yo, look, dude, this goes through the points, right?
Exactly.
That goes through the points. That one's a better fit. So that means some of the points need to be above or below the line.
Above.
Some need to be above the line, some need to be
Below.
below the line.
Oh.
So I want you to think about this. If I look at this residual, this point's above the line. Would that be a positive or negative residual? Positive. This point is below, so the residual would be negative. So some residuals are positive, some are negative.
Yes.
Any guesses what I would get if I add up all the positive residuals and all the negative residuals for the best line?
Zero.
Oh, I would get 0. How do I counteract that idea that some are positive and some are negative? Huh? Not square root, we have to,
Divided.
what did we do? We eventually took a square root, But when we were trying to find standard deviation, we had positive deviations and negative deviations. What do we have to do?
Bring them
Squared them, right? Remember how we squared the positive and made it stay positive?
No.
Joey, you don't remember this equation that we looked at? Standard deviation is the square root of the sum of x sub I minus x bar squared divided by n minus 1.
Oh yeah, this formula that you screwed up on the test.
Man, Joey, that's a really positive way to think about it instead of focusing on how you can grow and learn. Stop being so negative, dude. Your negativity affects your ability to learn and grow. Okay. We found those deviations and we squared them, didn't we? So why do you think we're creating squares? Because we're taking these residuals and squaring them. Because if you square a negative, you get a positive, okay? That's why these squares are coming from, and that's why these squares are important. So, no. I'm just connecting it to something you've already learned. Yeah. We're not going to use this formula, guys. I'm just connecting it to something you've already learned. That's why we're getting these squares. And so, notice right here where it says the residual is equal to the actual value minus the predicted. What's the actual value? The point or the line?
The point.
Remember, isn't the line a trend line predicting the points? That's a small thing that a lot of students miss. The actual points, those are the actual values. The line are the predictions. That's why if I take this value and I subtract the prediction, you see how that residual is above? So it's going to be a positive residual. Does that make sense? Kari, you good with that? Okay. Emily? Good. Joey? You good with that? Are you good with the prediction being the line and the actual value being the point?
What's that supposed to mean again?
I just explained it, bud. Were you paying attention when I was going over it?
I've been thinking.
What are you thinking about?
Because I have another doctor's appointment tomorrow, so I've been wondering how I'm supposed to do about my active collaboration score since we only really have 2 days.
Okay.
And I'm only going to be here for 1 day.
Talk to me after class about that. You're distracting yourself from learning what you need to learn right here and right now. Okay? Talk to me about that after class. Focus here so you can learn and grow. Okay. So it says examine the data point such that the year is 1950. What is the residual for this data point? So when I go to the year 1950, how am I going to find the year 1950?
You cover other points until you find it.
Yeah, but I mean there's an easier way. Where am I looking?
Why were 1950
Okay,
is on
so I go to
that?
1950 on the
You
X,
go up
and I go up.
until
Is it exactly 68?
68.1.
How'd you get 68.1?
It says it on the calculator.
Where does it say on the calculator?
Right beside 1950, and it's kind of like.
I was gonna say, I think, because that's what you need to pay attention to, you have to put the cursor over that point, is what I wanted you to see. And you'd already done that, but that's something you need to say, right? Did it originally say 68.1 when my cursor's over here?
No.
No, but if you put the cursor over that point, we see 1950, comma, 68.1. That is the actual life expectancy. Now, if I want the residual, again, you need to have a roadmap. How do we calculate a residual? This is the equation. It gives it to you.
residual equals the
Why are you looking at me? It tells you on the sheet, bro. You're making life harder than it has to be.
Actual value predict is bad.
Actual,
Value predicted.
so minus predicted. There we go. So the residual. What is the actual value?
68.1.
68.1 minus
The predicted.
the predicted. Do we have the predicted yet?
No. I don't even
Say
know.
again, Emily.
Whatever the point is at 1950 on the line.
Oh, so whatever the point is at 1950 on the line.
So 60.
So that looks to be about 60. Honestly, I got no clue. Anybody know how I could get what that Y value is?
You count up the point.
But remember, I'm not looking at these points anymore. I'm looking now at the line. Remember, the line is the prediction.
He was
Maddie? No, don't you dare assume. Excuse me, hold on. I got multiple people talking. Kari, let's start with you. Maybe. But I'm going from 60 to 68, right? So 62, 64, 66, 68 maybe. So maybe about 66? Aiden, what, is that what you're going to say? Yes?
I was 66 or 67.
Okay. Nathan?
I was going to say count by twos.
Yep.
Even.
So remember, what we're trying to find is the residual for 1950, right? That's what the directions say, residual for 1950, number 2. So I found that this point, 1950, has 68.1, so the actual life expectancy is 68.1, right? But I still need the predicted. Hey guys, how did we earlier in the book, in that lesson from the book, how did we find the predicted value based on an equation?
Oh.
substituted.
We substituted, right?
Yeah.
What could I do I have an equation I can substitute in for?
Yes.
Which equation?
The residual.
The 3.69 times 450.
Isn't that an equation I can substitute in for?
Yeah.
What could I substitute in for x, you know, the year?
1950.
Oh, let's substitute in 1950 into that equation. Now, remember, you can hit the little calculator button between escape and tab, and that's going to bring up your scratch pad, right? So you can type in 1950 on here in that scratch pad.
Oh my God.
Well, it's not just that. Remember, we're looking for the residual of 1950, right? So I went to the point, and so it'd be a little bit different for you, but I went to the point of 1950. See how it has 68.1? And then you need to find the predicted value, which I probably have a little bit different of an equation, but could you put 1950 in for x now? Okay. So you just have to put the cursor over that point and it tells you what the point is. Does that make sense? No, we're looking for year 1950. So we go to 1950 and we go up to that point. Well, so I just go to, again, I go to 1950, right? And there's a, right there, and so, well, remember, the whole thing is we're now using this equation to get the predicted, right? So the whole point is that the line is the predicted, so all I have to do is put in the input to get that predicted. All right, let me clarify a couple things. If I can get your eyes up here. Please remember, all right, because I'm just looking for 1950. So, hey, right here, eyes here, eyes here, eyes up here. I have 1950, that's all I know, and I need the actual value minus the predicted. What is always going to represent the predicted values? Or someone say it over here. The line. This line, isn't it predicting those outputs?
Yes, sir.
Okay, that trend line is my prediction. Okay? So if I know that I need the prediction for 1950, that's an x value, right? I can just substitute 1950 into the equation. Okay? Maddie was asking, how did I get this point? Well, I went still to the year 1950, and I know the prediction is always on the line. So I went to 1950 and I went to the line because that's what is predicted. But I know that I can always substitute my input into the equation as well. So what predicted value do we get when we substitute that 1950 into this? 62.8?
How do you get that?
64 point.
Joey,
That's it.
we have an equation here.
I don't understand what it means.
Okay, Joey. The calculator is giving me the equation. Please understand me here, guys. Look, we're going to break this equation down in a second. But the calculator is giving me the equation. And so when I look, this equation is for the line. I didn't have to do any work. Hey, Code, I appreciate that, but wait till small group time to explain that. I need them to hear this. This line, well, I put in, but the calculator automatically gave me the equation. You don't have to know anything besides the calculator's giving us the equation for that. Okay? And so if I want any of these predicted values, I have to substitute into the equation. Do you understand that? Okay, I'm going to come and talk with you when I get them started on the next thing. Look, regardless, I have a value, I subtract the predicted, and what do I get? That can't be 62.8.
It's 64.55.
Yeah.
That's more believable. 64 point what?
55.
Does anyone know why I knew that couldn't be 62.8?
Because it was,
Right. 62 is here, 64 is here. 62.8 would be like here. That's definitely not 1950, is it?
No.
No, it's 1940. Okay. So be careful, substitute into the equation correctly, but all you had to do is substitute 1950 into that equation. So what is the residual value there? So remember, I just need the actual, I subtract the predicted. Jada, do you even have a calculator in your hand, dude? Yes, Mary Lee.
3.55.
3.55? So you used your equation, and that's perfectly fine. That's how. I was asking based on that equation I had up there. Yeah. Okay, so one thing I do want to clarify, hear me very clearly on this. Hey, go, eyes up here. This is my trend line. So Coda got 62.8 earlier because she used her trend line. Could we all have slightly different trend lines? Yes, which is why we need to learn about the best trend line, right? And so that's something I want you to understand. We can each have slightly different trend lines. It would give us different residuals. That's why we need to learn how to find the best trend line. The 64.55, is that based on my equation? Yes? Okay. Alright. So what does this point mean? Well, it's a residual, right? But what is that residual telling us? Look back here. Well, it's telling us that the actual value is what?
68.
This is not telling me that the actual value is 68.1.
it's telling you that,
What are you saying? Okay. Why are you scared? It's just a thinking thing. Eyes up here. Look. Matt or Taylor, Peyton, y'all way back there? They're out cold. Trent, can you just give them a chance? There we go. Taylor, not like that. That's unnecessary. Unnecessary roughness. All right. So I want you to look at the actual value. Is that actual value above or below the predicted value? The actual's up here, right?
oh,
Oh, yes.
Oh, below.
So for me at least, it's above.
yes.
The actual is above the predicted. How much is that actual value above the predicted?
3.75.
Oh, this residual is telling me how much above it is?
Yes.
Yes. 3.55.
Okay, I'm going to come over here and say it. So say that one more time, then say it a little bit louder. Oh, look at that equation. Look at what Cardi just said. Is that telling us the difference between the actual and the predicted?
Yes.
Yes? If I look over here